First order transient circuits that contain a single capacitor or a single inductor with a resistor and maybe a voltage or current source can be solved with a general solution. In this video, I'll cover what this general solution is and why we can use a general solution to solve such circuits. So I'll start off with the natural response of an RC circuit in here. So in this circuit, we have the switch is at A for a very long time. So the source here, it charges the capacitor. So the capacitor stores some energy, and at some sort of a time 0, t equals 0, actually the switch goes to B. And then what we end up with is just a circuit that contains a capacitor in a single loop with another resistor in here. And this is just a natural response of an RC circuit. The capacitor will just naturally give its energy to the resistor. And we can describe this circuit with a single differential equations. For example, if I can say, well, this is here, I can call it I of C, and I can call this here I of R, for example. They're the same. So I can just say basically IC, which is a function of T, equals I of R, which is also a function of T. And if I can decide that this here between here and here is the voltage V of T, we know that the I of C is just simply C dV of T divided by D of T. But based on passive sign convention, this current in here is actually hitting, if you think about it, it's hitting the negative first. So what we need to do is we need to put the negative sign in here. And then we can say it equals I of R, which is just simply VT divided by R. We can rearrange the terms. What we get is dV of T divided by D of T plus 1 divided by RC V of T equals 0, and that is the differential equation that describes this particular natural response of an RC circuit. And what we see is we have a function v of t and its derivative, the first derivative, and that's why it's first order differential equation. So we can also rewrite this equation, this first order differential equation, instead of using v of t, we can rewrite it to be in terms of I of t, or the current flowing through the circuit. And I can basically just say this is here, it's just simply I of t. IR or IC or I of t, it's the same current since it's a single loop. So what we can say is, well, we know that I of t is just simply V of t divided by R using Ohm's law. This is basically from here, and of course it's going to the positive side, so positive is appropriate. Then what if we take the derivative of both sides? What we end up with is di of t divided by d of t equals 1 divided by R d V of t divided by d of t. I just took the derivative of both sides. And then what I can do is I can just basically say, well, I'll multiply by C in here and C in here. Basically, I didn't change anything. So, well, what we know is the following. So this here is, well, based on that, is just simply the current flowing through the capacitor, which is, we just call it IC of t, which is simply IC of t. So I can rewrite this one here as the following. We can rewrite the whole thing. Let me just move in here. What we will get is di of t divided by d of t equals 1 divided by RC. And this one here is just simply negative I of t. Why is it negative? Because of the passive sign convention. You see this one here, we have a negative in here. And what I have is I have C dV divided by dt. That's what I have in here. It's just simply negative IC of t. And that's basically what we have in here. So we do a little bit of algebra and we move the terms. What we end up with is di of t divided by d of t plus 1 divided by RC I of t equals 0. So this is another first order differential equation that describes the same exact circuit. This one is in terms of I of t. This one, well, the first one is in terms of v of t. This is in terms of I of t. So if you pay attention to both of them, you will see that they are of the same form. And that form is just simply dx of t, which is basically either x is either voltage or current divided by d of t, plus 1 divided, in this case, it's RC, which we know for RC circuits is tau. And this is basically is x of t equals, in this particular case, in both cases, happen to be 0. You can do the same type of analysis for all the other ones as well. So for example, if I can just say basically I have the natural response in here for these two circuits, and I have the step response for these two circuits in here, and then these are the RC circuits in here, and these are the RL circuits. So what you will see that if you spend the time to write the differential equations, the following. So we spend the time to write these two differential equations. You can write the one for the step response of an RC circuit. You're going to get pretty similar things, dv of t, and then there's 1 of tau and v of t, but now here and the out, like on the other side, instead of being 0, it will be vs divided by rc. The current happened to be exactly the same in here. So if you take a look at the RL, it's the same thing, but now the current We start with the current because inductors oppose the change of current, and then in here we have something similar. So if you take a look at all these differential equations that describe all these circuits, again, they're of the same shape. They're of this particular shape, which basically tells me that you have dx of t, some derivative of some sort of a function. That function could be v or I, the current or the voltage, okay, plus 1 divided by tau. Well, tau in the RC circuit happened to be RC, In here it will be L divided by R for our L circuits, multiplied by the x of t, and that will equal some sort of a kappa constant. So sometimes it's 0, sometimes it's not 0. Sometimes it's 0, sometimes it's not 0. And you can see they are zeros sometimes and others it's not. So all these circuits, natural or step response, RC or RL, pretty much have a same general equation that describe the current or the voltage. So as it turns out to be that this particular equation, because it's a first order differential equation, we can just basically take a general solution. A solution for the one basically gives me a solution for all, and that's what the general solution. So let me walk you through this general solution here. What do I need to do? So what we're going to do is here's the equation that describes them. So let me just go through them. So here, what I will do is I will say, well, what if t tends to infinity? Basically, if you wait for a very long time after switching, what we do is we'll get steady state in here. Okay, so everything will be at steady state. Well, if everything is at steady state, that means the x of t, whether it's current or voltage, will be just simply 0 because everything is at steady state, nothing else changing. And this particular general solution, by the way, applies to circuits that contains DC sources only. So that's why we can actually have that general solution. But anyway, nothing changes with time at infinity. So what we end up with is the following. 1 divided by tau, x of t, equals kappa. Okay, that means simply x of t is simply kappa times tau. But now this is not x of t anymore because it's not changing with time. So what we can call it is x final, the final value of x, basically. Whatever x is, it could be voltage or current. All right, so now that's good. So we go back to this equation in here. So let me just do a little bit of algebra on this equation in here. Okay, so what we have is dx of t divided by d of t is equal to kappa negative 1 divided by tau x of t. So I'll do a little bit of algebra in here, and what we will do is we'll say, well, this one here we can just simply say negative x of t plus kappa tau divided by tau, and that will be dx of t divided by d of t. All right, but we know that this one here is just the final value of x. So let me just substitute this. Dx of t divided by d of t is just simply negative x of t plus x final divided by tau. Okay, so now what I will do, it's a first order differential equation, so what I will do is I'll just isolate the x's together and the t on the other side. That's what we're going to do. Okay, so the way we're going to do it, we're going to say this is here dx of t divided by, and we can just simply say, actually we can just basically say this is negative, this is positive in here, and this one here is negative, just to simplify things. So that will be x of t minus x of f, okay, equals negative 1 divided by tau. So I kept the negative here, basically I just took it out, okay, times d of t. And if we take the integral for both sides, what we will end up with is the following. This is I'm going to change the variable in here because I'll use x of t in here, and I'll use xt of 0 in here. That will be, instead of x, will be u of t minus, well, x of f is just a constant in our case, negative 1 divided by tau, from d of v, for example, or y, or whatever we want to call it, and this one here is from t0 to t. We take the integral for both sides. What we'll end up with is the logarithm of pretty much u of t minus x of f, okay, and this one here is evaluated at x of t, and this one here is x of t0, and that equals negative 1 divided by tau, and hopefully you get that this is t minus t0. So this one here is just simply x of t minus x of f, and this one here is x of t0 minus x of f. And I can just, instead of x of t0, just to simplify things, I'll just basically say initial, which is x of 0. It's the same. So let me just write it in here. I can just say x0, which is the initial value, Okay, you can keep it at xt. Well, why don't we keep it at t0 just so that nobody gets confused. X at t0 equals -1 divided by tau, and that's t minus t0. All right, so we continue. We take the exponent for both sides. What we do is x of t minus x of f divided by x of t0 minus x of f equals e to the -1, or actually we can just say t minus t0 divided by tau. All right, so what we need is x of t, and that will be simply x of f plus, yes, we moved that one here, x of t0 minus x of f e to the -t minus t0 divided by tau. And that here is a general solution for that first order differential equation that we described. No matter what the x is, no matter what the f is, it's the same. So let me just respond to it or explain it. So what we have is x of t represent the voltage or current in a circuit, some sort of a voltage or current that you have. What you need to do is we need to find the final value of it, basically after switching for a very long time. If you, after switching, you waited for a very long time, what would be that value? This is the same value in here. And maybe right before switching or right at switching, you just have to figure out the initial current or voltage. And then also what you need to do is you need to find what the tau is in here, which is either RC for RC circuit or maybe L divided by R for RL circuits. And of course that contains R in both cases, and that happened to be R, maybe sometimes it will happen to be R Thevenin, so you have to compute this. So let me just summarize this general solution steps down. So if you end up with a circuit that is a first order differential equation or a first order transient circuit described by first order differential equations of this form, and it has sources that are DC sources, the general solution is of this form in here. So the step you need to take is the following. So what we need to do is you identify the variable of interest, x of t. So that x of t can be an I of t or can be v of t, depending on the circuit. Sometimes it's asked from us. Now, recommendations that are not necessary, but they're recommendations. So if you're dealing with RC circuits, maybe x should be v. If you're dealing with RL circuits, maybe your x should be I. And the reason why is because initially the RC, the capacitor, does not change the voltage across it, and the inductor does not change the current. And this is basically refers to the V across the capacitor. This is I across the inductor. All right. Next step, or basically if you figure out which one you want, what you need to do next is to figure out, well, let's figure out what the initial value of that variable that we decided. If the variable happened to be a current, what's I of t0? If it happened to be voltage, what's a V of t0? So you basically select which one it is. And again, if you're across a capacitor, it's easier to do with a V, but not necessary, but it's easier. If you're an inductor, it's easier just to do it with I of t. And then once you figure out the initial value, you say, well, after switching, what happens? You just basically wait for a very long time, and you treat the circuit as if the capacitor is an open circuit or the inductor is a short circuit, and then you figure out the x of f, well, the final value of the current, the final value of the voltage. That's what you do. And then lastly, basically we figured out all of these in here. So lastly, what we need to do is we need to figure out the time constant tau. We know for RC circuits RC, and for RL circuits it's just simply L divided by R. So this R in here, it might be R Thevenin. So you might have to find the Thevenin equivalent resistance, and that's what you need to do in order for you to figure out what the tau is for both. Then you go ahead and you just substitute in here, and you will have the general solution for whatever first order circuit you have.